Hey everybody, Mr. Judson here. So we've done most of what we need to do in Chapter 2, but there's one idea that kind of works or uses derivatives to help solve limits. Now we couldn't do this in Chapter 1 because we didn't know how to do a derivative yet. So we'll go ahead and pick this up here. And it's called Hopital's rule. It basically says this. It says if the limit as x approaches c of f of x over g of x, if that equals 0 over 0 or any combination of plus or minus infinity over plus or minus infinity. All right? 0 over 4 doesn't work. It's got to be 0 over 0 or some kind of plus or minus infinity over plus or minus infinity. Okay? If that happens, then that limit is really equal to the limit as x approaches c of f prime of x over g prime of x. And so what that means is if I just take the derivative of the numerator and the derivative of the denominator and then do the limit, it works. It gives us the same answer. Now we got to be real careful about one thing here. Okay? We're not doing a quotient rule for this. We're just doing derivative of the numerator and derivative of the denominator. But the problem with this rule is once we do it, people think that's how you take the derivative of a fraction. No, we still have to do the quotient rule if we're doing the derivative of a fraction. We're doing a limit here, and so this is different. We've got to make sure we keep that straight. Okay? All right, so let's try an example. All right, so I've got the limit here as x approaches -1 of 2x squared minus x minus 3 over x plus 1. Now, first step is we have to verify that one of these two conditions here is met. I don't want to just look at this and go, oh, fraction, take the derivative, now try the limit. You know, I got to make sure I get one of these two things for an answer in order to use this rule. So if I plug in a -1, I'm going to get positive 1 times 2, that's 2, minus a -1, that's 3, minus 3, that's 0. And if I do the same thing here, plug in a -1, I get 0. So I did get 0 over 0. This meets the condition. So that means that this is going to equal the limit as x approaches -1. Remember, you got to keep on writing down the limit until you actually plug that number in. So the derivative of the numerator is going to be 4x minus 1. And the derivative of the denominator is going to be just 1. I'm not going to get 0 over 0 again, right? I get 1 in the denominator now. So now I just need to plug that -1 in and see what I get. So -4 minus 1, that's a -5 divided by 1. Answer is -5. Okay. This shows up a lot on the Central Washington test, limits where we can use this rule. And so I think that's probably something that we should think, I want this in my head. I want to know this rule when I sit down and take the Central Washington test in late January. Okay? Let's try another one. All right, so this one almost looks like one of our special limits, except this angle and this expression have to be the same. We could actually make that happen, but maybe the Hopital's rule is going to be easier. All right, so you guys go ahead and try this with the Hopital's rule. All right, so if I plug a 0 in, I definitely get 0 here. I'm going to take the sine of 0, which is the y-coordinate. It's right on the x-axis, so that's 0. So I did get 0 over 0. Okay. I think if I'm taking the AP test, I need to make sure and say, you know, something like this if it's on the written part, and therefore this equals the limit as x approaches 0. Now I'll do the derivative. Derivative of sine is a cosine of 4x times the derivative of the angle, which is just 4, and the derivative of the denominator is 2. Okay? So I just thought of something. You know, some people might look at this and go, Judson, how come you're not putting your dx's and dy's and stuff in there? Well, because it's not an equation where I can't get y by itself. I'm just taking derivatives of, you know, two things that are sitting there. So I'll use the normal derivative rules. Okay, we don't have to take the derivative implicitly. All right, so I'm no longer going to get 0 here, so I won't be able to do this again. If I plug a 0 in here, I've got cosine of 0, which is 1 times 4 over 2. And so my answer to that limit is 2. Had I done this with our special limit, I would have said, I want to make this equal 4x, so I'm going to multiply this by 2, and you got to do the same thing to the top. And so now I know that the sine of 4x over 4x, the limit of that is 1, times 2 is 2. So just another way to get to that answer. All right, you guys go ahead and try this one. All right, so if I plug a -1 in, yeah, I'm going to get 0 in the denominator. Here I get a +1. Subtract a -1, that means plus 1 more, that's 2, minus 2. So yes, I get 0 over 0. So now this is going to be the limit as x approaches -1 of 2x minus 1 over 1. And so now if I plug that -1 straight in, I get a -2 minus 1, that's a -3 over 1. There's my answer, -3. So I like this rule. Kind of makes things just a little bit easier. This happens occasionally. You go through and you take the derivative of the top, derivative of the bottom, and you get 0 over 0 again. And when that happens, then you just do Hopital's rule again. Okay? Let's try one more problem. All right, so I'm going to let you guys try this, but I just want to say one thing first. When you plug infinity into here, into this numerator, it looks like you get infinity minus infinity, which seems like it would be 0 if we really knew what infinity was. Well, I'm not sure if that happens. If I take infinity and square it, and then multiply by 3, I get a much larger infinity than I do over here, if that makes sense. All right? So you kind of just want to focus on the leading term, the one with the highest exponent. That's the dominant term. And we're just going to think when we plug infinity in here, we're going to get infinity over infinity. We should use Hopital's rule for that. Okay? So you guys go ahead and try. All right, so I do get infinity over infinity. So that means I can take the derivative of each of these. So the limit as x approaches infinity. Here we're going to get 6x minus 2. Down here I'll get 2x. And so if I do the limit again, I'm going to plug in infinity here. 6 times infinity, really big number, minus 2, still a really big number. And here I've got 2 times infinity, so a really big number. So it looks like infinity over infinity again. So I need to do the Hopital's rule again. And so that means that this thing is now going to become the limit as x approaches infinity. Derivative of the numerator is 6. Denominator is 2. There's no place to plug an infinity in anymore, so the answer is just 6 over 2, which is 3. There it is. All right, that's it. So not a real difficult idea today, but a really important idea. This makes problems easier. Every time we did a limit in the first chapter, I kept on looking at it going, oh, we can do Hopital's rule. But we didn't know how to do derivatives yet, so we couldn't apply that. Now that we know how to do derivatives, we can use Hopital's rule. All right, let me get you guys a homework assignment. All right, so still on week 12, this is Thursday's version. We're on page 369. We're going to do 7 to 18, 25, 27, 31, and 33. One of the things you'll notice, well, first of all, we skipped a whole bunch of pages. And that's because Central Washington does this with their derivatives. But you'll also notice there's a lot of problems here that we kind of skipped over, ones that have natural logs in them, or e to the x, things like that. We just haven't learned that yet. So we'll just do the ones based on what we've learned. All right, you guys, that's it. That's all I have. You have a good day. Take care. Stay safe. We'll see you next week. Bye. Don't forget, exam on Thursday the 10th. And you guys want to make sure and email me and let me know what time you're taking that exam. Are you doing it during class, or are you doing it at 6:30 in the evening? I moved the evening test a little bit later because ran into some issues with parents getting home on time. And so this will help them out a little bit. All right? All right, we'll see you guys later. Bye.